Oh yeah, hello everyone. We'll start today's session in a couple of minutes. We're waiting if somebody, a few more people will be joining this session. Okay, yeah. So good evening everyone. Here I am Diljit Datta. I am a research scholar at Indian Institute of Science. So yeah, we'll be starting today's problem solving session on the course Hydraulic Engineering, which is being taught by Muhammad Saad Afzal from IIT Kharagpur. So let's get started. So yeah, in this session we will be covering three topics. That is, first we will see what is Moody's diagram, and secondly we will be seeing what are the minor losses Moody's diagram, that is for circular pipes. Then secondly we will be seeing the minor losses and how are the minor losses arising in case of pipes. And thirdly we will see pipe connections and pipe networks, like parallel connection of pipes or series connection of pipes. And then lastly we will see the pipe networks and how we can solve a problem related to pipe networks. Okay. So coming to the first topic, we will see what is Moody's diagram. So what is Moody's diagram? So it is actually a non-dimensional graph that relates the Darcy-Weisbach friction factor and Reynolds number of FD, the Reynolds number RE, and the surface roughness of the fully developed flow in a circular pipe. So this thing is important. This diagram is valid only for a circular pipe. It is not valid for a pipe of any other cross section. So how is this diagram, the Moody's chart or the Moody's diagram developed? So this was developed by a series of experiments that was being conducted by Nirukutse. So what he took sand. So he took some sand grains which had uniform grain parameter, which is uniform parameter, that is surface roughness parameter K, and then he also took uh, he also and also the sand grain had uniform diameter. So the roughness as well as the roughness diameter of the sand particles was same. So to find K, K is the height of the roughness. That is like, suppose if you want to explain in simple terms, so there will be this pipe material. If it is a circular pipe, this pipe material will have roughness like this. So the height the height of the roughness is called K, average height. So a series of experiments was carried out for a pipe, and at very large Reynolds numbers, that is when a flow is turbulent and the boundary layer is extremely small, and the friction factor F was found out from Darcy-Weisbach equation, that is FLV squared by 2 GD. Like HF equal to FLV squared by 2 GD. Now the friction factor that was obtained from the Darcy-Weisbach equation was substituted in the Karman-Prandtl equation, and this following empirical relation was obtained, that it relates 1 by root f equals to 2 into log of r by k plus 1 by 1.74. This is valid when the flow is turbulent. So for turbulent flow, the friction factor doesn't depend on the Reynolds number. F depends only on the relative roughness. Relative roughness is r by k. What is r? R is the radius of the pipe and k is the roughness height that I already mentioned. Now in a Moody's diagram, what we do, we plot friction factor F and the Reynolds number Re. So we plot friction factor F in the y-axis and the Reynolds number Re in the x-axis. And when we take extremely smooth pipes, in that case you can see that the friction factor is a function of Re, that is F is equal to 64 by Re. For laminar flow, and you can see for smooth pipes, you can see that the value of F is decreasing as the Reynolds number is increasing. Now this is for laminar flow. Like when it is laminar, you can see it is almost the inverse hyperbolic relation. Now in case of a complete turbulent region, now this is a suppose if we take this area as the complete turbulent region, so in this case you can see as the Reynolds number is increasing, the friction factor F is not proportional to the Reynolds number, it is not depending on the Reynolds number. So in that case, for rough pipes, for pipes in turbulent flow, the friction factor is function of only r by k, and that relation we can obtain from this graph. We plot Re into root f by r by k on the x-axis and 1 by root f minus 2 log r by k on the x-axis, and from that we will get the, for two types of pipes we plot, one is for the smooth pipes and other is for the rough, completely rough pipe, and thirdly we have the pipe with suppose for the natural roughness. So then we obtain a empirical plot like this as mentioned in this figure. yeah, we can. This is one thing, and secondly, what we can see for the smooth pipes, the variation in the friction factor which Reynolds number is more. It follows a hyperbolic curve for laminar as well as for the turbulent region. But when you go to rough pipes, the variation with Reynolds number is extremely less. So these are some typical values of the roughness parameter K, that is for like metals like steel, wrought iron, copper, glass. These are very smooth materials, so for that we will have the roughness parameter as very less. Now for concrete, cast iron and riveted steel, we will have roughness parameter as very high value, that is close to 1. That is close to 1 millimeter. Now what is the use of Moody's diagram? So use is that, like, if we know the Reynolds number of the flow, and also if we know the relative roughness, radius of the pipe, and the roughness parameter of the pipe material, then we can estimate the Darcy Weisbach friction factor F. So the Moody's diagram is used to obtain the value of F from this graph. Okay, so this was all about Moody's diagram. You just need to remember 3 main things. First thing is, what is the use of Moody's diagram? So the use of Moody's diagram is to get the value of friction factor when for smooth rough pipes and for different materials, as this is already prepared for all the different types of materials.
सॉरी, मुझे इंटरनेट से कनेक्ट करने में परेशानी हो रही है। शायद रूटर या एको डिवाइस में कोई समस्या है, इसलिए उन्हें रीस्टार्ट करें। दोनों का प्लग निकाल दें, फिर रूटर का प्लग वापस लगा दें। 30 सेकंड इंतज़ार करें। जब रूटर चालू हो जाए और इंटरनेट से कनेक्ट हो जाए, तब एको डिवाइस का प्लग वापस लगा दें।
Okay, sorry for the interruption. Okay, and yeah, so next we will see what are the losses in pipes, and for different types, what are the different types of losses. So one first type of loss is the, like, when there is a sudden contraction in a pipe. So this you can see there is sudden contraction. So in that case, the streamlines will be encountering some sudden change in the diameter of the flow. So there will be, it will be hitting these surfaces, and there will be losses, eddy losses, that will be taking place. And so the head loss that is taking place from section 1 to section 2 is given by this formula. It is 0.5 v2 square by 2g, where what is v2? v2 is the velocity in the subsequent section, so that is after contraction. Now if there is a gradual contraction, that is from v1 to v2, there is an angle, and based on the angle the head loss will be different. So if the angle is 30 degree, then we will have around 0.2, because there will be the eddies formation will be very less. It is as the weight is smoothly vary. As the angle increases to 30 or 40 degree, the head loss will be more, and in this case the head loss will be function of both v2 and v1. Then thirdly, this is the loss due to sudden enlargement. Like, what happens in a sudden enlargement? So the thing is that when a flow is taking place, suppose smoothly, and then you suddenly enlarge the pipe, now instantly the streamlines cannot take this kind of path. Okay, so it takes the diameter over some time and some distance, and in between there will be some eddies or non-linear dissipation, and this dissipation leads to some losses in sudden enlargement, and this is and the head loss due to sudden enlargement is given by h equal to KL in V1 squared by 2G. And how we can find KL? KL can be estimated based on the area of the two cross sections. It is 1 minus A1 by A2 whole square. Therefore, head loss equal to V1 minus V2 whole square by 2G. Now, this was all about sudden expansion and sudden contraction, or gradual expansion and gradual contraction. Similarly, if there is a gradual expansion, the losses will be less. Now, there is a need to find out what are the head loss when there is a pipe entrance. Now, pipe entrance is like when you are using a pipe to for when the water is flowing through a pipe, it has to come from some reservoir or some tank. So based on how you fit the pipe to the tank or the reservoir, based on that fitting or type of fitting, there will be different head losses. So there can be 4 different types. First is when the pipe is at 90 degree and it starts exactly at the end of the, it is exactly at the wall of the reservoir or the tank. Second is the pipe is inserted slightly in between, it is slightly from in between and from for some distance from the wall. This is case B. So this case will have highest amount of head loss. Why? Because there will be, as the water is flowing, so there will be some streamlines that will be going to the pipe, but there will be lot of streamlines that will also be hitting the pipe here and causing energy losses. Then thirdly is like there is a smooth variation of the wall and then the pipe is fitted like that. In this case, the streamlines will be going smoothly inside the pipe, and so the head loss will be less, so the coefficient will be less. And lastly, when the pipe is fitted at an angle, so based on the angle, the head loss will be more or less. So this was at pipe entrance. Just remember the 4 cases, like when head loss will be more and when head loss will be less. So this might come as a MCQ, multiple choice question in competitive examination like GATE or IAS. And next is like head loss at a pipe exit. So when we are filling a reservoir or tank using a pipe, in that case, how the pipe is fitted to the tank, based on that there will be head losses, varying amount of head loss. Similarly, here also the highest amount of head loss is when the pipe is inserted for some distance inside the reservoir. That is case 1, first case. Okay, so in this case, so for the case of pipe head loss at pipe exit, so whether we fit the pipe at any angle or we fit the pipe slightly inserted or we make a gradual expansion, it doesn't matter, because finally the pipe velocity will be coming to rest. So if there was some velocity of the water, suppose v, then after coming to reservoir the velocity will be 0. So the head that was there, entirely the kinetic energy will be converted to potential energy, so there will be loss of head. So the head loss will be v square by 2g and the coefficient will be 1. And then the last case is the pipe head loss in pipe bends. So what happens in bends? So as the water is flowing like this, it will hit the surface, and this will cause some losses in pipe bends, and based on the angle of the bend, the amount of head loss will be less or more. And also it depends on the r by d, that is the radius. So depends on the radius of the pipe bend to the diameter of the pipe. Radius is like, so the bend will be a part of a circle, so the radius of r is the radii of curvature. R is the radii of curvature, and d is the diameter of the pipe. So based on the radii of curvature and the diameter of the pipe, the head losses will be different. So any doubts still here? I'll wait for a minute and then we'll continue to the next section. Now we will see the combination of pipes, how pipes can be combined in series and or parallel, and what is compound pipes. So when the first case is, okay, so the first case is the when pipes are connected in series. When one or more pipes are connected in series, so what will be the case? So this is case like this. One pipe, now the discharge that will be passing through its pipe will be same, since both all the three pipes are conveying the same amount of discharge. So but what will be different? The head losses will be different, and the total head loss between from the end, from the start to the end, will be the sum of the head losses in the pipe. So one case is of 0.5 v square and v1 square by 2g will be the head loss at the entry. It is loss at pipe entry. So this is the head loss at pipe entry. Then the FL1 v1 square by 2g d1 head loss at pipe 1. This comes from Darcy-Weisbach equation. Similarly, then 0.5 v2 square by 2g. So this will be head loss at this part by 2g, head loss at pipe entrance 2, and then FL f2 l2 v2 square by 2g d2. And similarly, these head losses can be continue for the number of pipes we are connecting in series. and but the discharge Q will be A into V, so it will be same for all the three pipes. Now if we neglect the minor losses, then we can assume that the head loss, total head loss, is the sum of the friction losses, that is from the Darcy-Weisbach equation. Okay, so this is pipe in series. Now if we want to replace these three pipes as an three separate pipes of different length and different diameter, if we want to replace these pipes as a single pipe, then we call it a compound pipe. And what will be the diameter and the length of the compound pipe? How do we find that? So to find that, we will be using this equation and the continuity equation. So the total head loss is this, that is sum of all the head losses. Now from continuity we have that all the discharges are same in all the three pipes, and we assume that the friction factor is F, same for all pipes, that is all the pipes are made of same material. In that case the friction factor will be same. So the total head loss will be, if we substitute, it will be F Q square by 2G pi by 4 to the power whole square, L1 by D1 to the power 5, L2 plus D to the power 5 plus till the number of pipes. And this is for the compound. If we replace this all the pipes by a single pipe, then the head loss will be F into L is the length of the equivalent pipe, and D is the dia of the equivalent pipe. So L by D to the power 5 equal to L1. So if we equate both these equations, we will get L by D to the power 5 equal to sum of the L1, sum of the ratios of the other pipes, that is pipes in series, as L1 by D1 to the power 5 plus L2 by D to the power 5 plus all the terms. So this equation is called the Dupuit's equation for equivalent pipe. Okay, I hope this is clear. So this was about when pipes are connected in series. Now the next case is when pipes are connected in parallel. In this case, what will be same? So the discharge cannot be same, because whatever Q is coming, it is divided into two parts. So Q will be sum of the discharges, that is Q1 plus Q2, but the head loss through each pipe will be same, since the end point and the starting point are the same, so the loss in head will be same. However, in whatever way we connect the pipes from the end point and the starting point, it doesn't matter, the head loss will be same, since the head loss is the change in the total energy line. So the change will be same, and depends only on the starting point and the end point. So HF equal to F L1 V1 square by 2G D1 equal to F L2 V2 square by 2G D2. Okay, so this is how the head loss varies. a parallel, pipes connected in parallel. Now there is something called the flow through a bypass. So when we talk about flow through bypass, what it exactly is? So this is done to find or evaluate the flow or the amount of flow when it is taking place in a very large pipe, like when suppose a pipe is connected from a reservoir or from a river to, and it is connected to a city, it is supplying water to a whole city. In that case we cannot put flow meters or in such large pipes. So in that case what we do, for two sections of the large pipe we connect a bypass and then we measure the flow in the bypass. If we know the flow in the bypass based on some relation with the main flow, we can get the total amount of flow in the main pipe. So this is the schematic of a flow through a bypass. So H1 is the head at section 1, H2 is the head at section 2. Then FLV squared by 2G. Now these two pipes are connected in parallel, so the head loss will be same for both the pipes. So if we will get a, so if we take capital V as the flow in the large pipe, capital D is the diameter of the large pipe, and small v and small d are diameter and velocity in the small pipe. So we will get the relation L V square by D equal to small r into small v square by small d plus K into V square, where K into V square is the loss at entry and exit, total losses. So based on that we get this relation, that is velocity of the two sections are related based on the diameter and the length of the two sections. So if we can estimate small v, we can get capital V. And if we want to read it in terms of discharge, so if you know capital Q equal to pi d square by 4 into capital V, small q equal to pi d square by 4 into small v, and if we take the ratio of capital Q and small q, we will get this final relation. Okay, so this is how a branch pipe is, how bypass is used for measuring flow in large pipe. Now there is something called the branch pipes. Suppose, so what is the like pipe branches? The thing is that suppose we have 3 reservoirs and we want to connect the 3 reservoirs by 3 pipes. So here is a schematic for that problem. So if we take reservoirs A, B and C, now these reservoirs are connected by pipes. All the pipes have the same material and they are connected at the junction D. Now we have to find out what is the velocity V1, V2, V3 and the piezometric head at D. So these are the 4 unknowns. So we will need 4 equations. So how do we get the 4 equations? So first up we will apply the Bernoulli equation from reservoir A to junction D. So if we apply that, what will we get? So at junction at A, at the surface of A, the velocity is 0. The datum head is Z1 and the piezometric head is, and the pressure head is P atmospheric, and if we are neglecting P atmospheric, if we are taking God's pressure, then P atmospheric will be 0. Excuse me. So the only term in the Bernoulli equation from A will be Z1. Now add D, what are the terms that we have. One, first we will have the datum head. So datum head will be, suppose we consider ZD. Then we have the piezometric head or the pressure head, it will be PD by W, the pressure at point D divided by specific weight of the fluid or water. And lastly there will be the velocity head, that is V1 squared by and lastly we will have the head loss term, that is the HF1, and this is head loss will come as FLV square by GD. Now similarly this was between the surface of A and D. Similarly we can apply the Bernoulli equation from the junction D and the surface of reservoir B. So we will get one relation there too, and similarly, and thirdly we apply the Bernoulli equation from junction D and surface of reservoir C. So finally, so these three equations we get, and the relations between the pressure head at D and the datum head and head loss, it is a friction loss, and lastly the continuity equation, that the whatever flow is coming from one, it should be distributed it should be distributed to 2 and 3, that is Q1 equals to Q2 plus Q3. So substitute for Q1, Q2 and Q3, we will get one more relation. So we have 4 unknowns and 4 equations. If we solve this, we will get the values of velocity, the V1, V2, V3, and the pressure head PD by W. Okay, so this was about branched pipe, how the branched pipes are connected. And last topic before solving the numericals is pipe networks. So what are pipe networks? You can see this is a schematic of a pipe network. Pipes can be connected, interconnected pipes, and finally it will form a loop. So this is generally a pipe system for a city. There are several distribution points in between. There is only one inflow and one outflow. So the main problem in pipe network is like what will be the flow in the different pipes in the network. So to find the flow in the different pipes, we have to see what are the conditions of the flow that needs to be satisfied in order to find the flow. So the first thing that we need to solve is the take care is the principle of continuity, that the flow into each junction must be equal to the flow out of each junction. That is, suppose if we take a junction C, then whatever flow is coming to C, the same amount of flow should be going out of C. So this comes from the continuity equation. Then second, in each loop, if we take one loop, the loss of head due to flow in the clockwise direction must be equal to the loss of head of flow in the anti-clockwise direction. So if we proceed in clockwise and anti-clockwise, the loss of head should be same. So this is the second condition, and the third condition is the Darcy-Weisbach equation must be satisfied for flow in each pipe. Minor losses may be neglected if the pipe lengths are large. However, if the minor losses are large, then they may be taken into account. Yeah, that is one thing. And So the head loss can be related in terms of the discharge Q as R into Q to the power n, where n is for the Seebeck equation, n is equal to 2 and R is the constant term and R is the proportionality factor, that is FL by 2GD, so that depends on length and diameter of the pipe and the pipe network. So in general, like if we have a large pipe network, it to solve the values of the velocities in the pipe, like in the pipes in the pipe network, analytically is a very complicated problem. So to make it simple, so there is a method called the Hardy-Cross method. So this was developed by Hardy and Cross, so the name only suggests that. So what do we do in the Hardy-Cross method? So what we do is, initially we assume a suitable distribution of flow. So whatever flow is coming, so we give some values to the pipe for the pipes that are connected to each junction, and we assume it suitably so that it is following the continuity equation as it was discussed in the main point number 1. Secondly, then what we do with the whatever value of Q we assumed for each pipe, we compute the head loss, and then we consider the different loops in the pipe network, and then we compute the net head loss around each circuit. Then we compute the net head loss around each circuit, and considering the clockwise head loss as positive and anti-clockwise head loss as negative. So this is an important thing. So when you are proceeding in the loop in the clockwise direction, we take the, and the flow is in, even if you are proceeding in a clockwise direction and the flow is in clockwise, then we take the head loss as positive, and if the flow is anti-clockwise, we take the head loss as negative. And in a loop from the starting point, if we, the net head loss will be 0. So in most of the cases, what will happen, like when you are assuming the value of Q, so there will be some mismatch in the values of Q since we are assuming it. So the flows will be corrected by adding a value of delta Q for each pipe till the circuit is balanced. So suppose Q is the actual discharge, then Q naught we have assumed some discharge, and then so the actual discharge Q equal to is assumed as Q naught plus delta Q, and delta Q can be positive or negative. So what is the head loss? So HF equal to R into Q to the power n. So this comes from the assumed equation for head loss, and if we substitute the value of Q, R into Q naught plus delta Q to the power n. Now for the complete circuit, that is for the complete loop, we will have the total head loss equal to sum of the total terms. So we add a sigma, and then the second term you can expand by binomial theorem. If we expand by binomial theorem, we will get a lot of terms, and the first term will be sigma r Q naught to the power n, and the second term will become a sigma r n Q naught to the power n minus 1 into delta Q. These are the leading order terms in the binomial theorem, and as we proceed further, the delta Q powers of delta Q will be increasing, and since we are assuming that delta Q won't be varying that much, from the delta Q will be very small, so the other terms we will be neglecting. Now for actual flow, the sum of total head loss will be 0, so this term should be equal to 0. So we can get a delta Q as minus of sigma r into q naught to the power n by sigma r into n into q naught to the power n minus 1. Okay, so now we see like how do we when we get the value of delta q, how do we correct the flows in the pipes, in the pipe network. So the correction of denominator is the sum of absolute terms, and hence it has no sign. If the head losses due to flow in the clockwise direction are more than losses due to flow in the anti-clockwise direction, then according to sign convention adopted, delta q will be negative, and hence it should be added to the flow in the anti-clockwise direction and subtracted for the flow in the clockwise direction. So if delta q is negative, we assume that for anti-clockwise it is negative. The flow is the head loss is negative. So we will be adding for anti-clockwise and we will be subtracting for the clockwise flows. And on the other hand, if the head losses due to the flow in the clockwise direction are less than the head losses due to flow in the anti-clockwise direction, then delta q will be positive, and hence it should be added to the flow in the clockwise direction and subtracted from the flow in the anti-clockwise direction. So once we have corrected the flows, we will do a second trial and we will again obtain the value of delta q. If delta q is like negligible, we will stop it there, and if it is not negligible, we will proceed for one more trial and we will see how the value of delta q is changing. So this is all about the Hardy-Cross method. What is the formula for determining the size of the equivalent pipe for two pipes? So we will solving some questions. What is the formula for determining the size of an equivalent pipe for two pipes of length L1, L2 and diameters D1, D2 respectively, where L equals to L1 plus L2. So these are series, and we have obtained repeat equation. What it says that the equivalent length of pipe will be distributed to the individual lengths by this formula. So correct answer is option D. next question is two pipelines of equal lengths. It is L1 is equal to L2, G1 is equal to 10, G2 is equal to 40, connected in parallel between two reservoirs. If the friction factor F is same for both the pipes, the ratio of discharges in the larger to the smaller pipe is F1 equal to F divided by L1. F2 will be HF1 equal to is in terms of the discharges. Q1 square by 10 to the power 5 equals Q2 by Q1 is equal to under root distance is 30. Now the third question. Three parallel pipes connected to the two ends have flow rates Q1, Q2 and Q3 respectively, and the corresponding frictional head losses are HL1, HL2 and HL3. The correct expressions for total flow rate Q and the frictional head loss around the two ends are. The pipes are connected in parallel, so Q is equal to Q1 plus Q2 plus Q3, and the head losses will be equal. So option is correct. Option is option. Three pipes are connected in series, and we have seen that when the pipes are connected in series, the discharge through its pipe will be same. So this is from continuity equation. Now two tanks are connected in parallel by two pipes A and B of identical friction factors and lengths. If the size of pipe A is double that of pipe B, then their discharges will be in the ratio of we have seen from the previous question that the discharges so it will be 2 to the power of 2.5 is around 5.66. At the junctions of any junction of any pipe network, the flow must satisfy the continuity equation. Without continuity, the flow cannot take place. The chart showing the variation of friction factor F with Reynolds number Re and epsilon by discharge is called the Moody's diagram. So we have seen what is the Moody's diagram. A piping system consists of three pipes arranged in series. The lengths of pipes are 1200, 750 and 600, and diameters 750, 600 and 450. Transform the system to an equivalent 450 mm diameter pipe. So we have from Dupuit's equation L by d to the power 5 substitute, and what will we have to find? The length. L1 is how much? So if we substitute these values, we will get L is equal to 71.2. For a laminar flow through a circular pipe, the maximum velocity is equal to 2 times the average velocity. This we have seen in the previous lecture only. Okay. Laminar flow through a circular pipe of diameter 20 cm, flow velocity at radial distance of 5 cm from the pipe axis is 0.75 meter per second. What is the maximum flow velocity in the section? So U by U max. So 0.75. So 1 meter per second. Correct option is option B. Okay, now I will be solving some problems from the book Modian Shed. So this is the first question. A compound piping system consists of 1800 meter of 0.5 meter 1200 meter of 0.4 meter and 600 meter of 0.3 meter new cast iron pipes connected in series. Convert the system to an equivalent length of 0.4 mm pipe and an equivalent size pipe of 3600 meter long. So how do we solve this? Say again, we will solve by Dupuit's equation. So L by D to the power 5 equal to L1 by D1 to the power 5 plus so for final L is equal to 0.4 to the power 5 equal to 1800 by 0.5 to the power 5 plus so the total term will be 4.318 meter. Now to find D for L is equals to so total D will be coming as 0.39 meter. Okay, so this was the first question. Now we solve a second question based on pipe networks. So for a distribution main of a city water supply, a 0.3 meter main is required. As pipes above 0.25 meter diameter are not available, it is okay. So for a distribution main of a city water supply, a 0.3 meter main is required. As pipes above 0.25 diameter are not available, it is necessary to lay two parallel mains of same diameter. Find the diameter of the parallel main. So how do we proceed? So we know HF equals to FLV square by 2GD. Now the velocity can be termed often found out from this equation as d by. Now the discharge can be found in how? By if we substitute for velocity, we will get around hf into 2g by half into d to the power 5 by 2 divided by L to the power half. So this is velocity from for each pipe. This is discharge for each. Now we know that for parallel connection, total discharge equals to Q1 plus Q2. And it is given that pipes above two parallel mains of same diameter, so Q1 is equals to Q2 here. So in that case, 5/4 under chef. Equals to 2 into, this is the total head loss, total K is equal to 2 into 5/4 into HF into 2G/F. Capital D is the diameter of the equivalent pipe. So d to the power 5/2 is equals to 2 into d to small d to the power 5/2. Therefore, small d is equal to d by 2 to the power of. So this is for two pipes. If for n number of pipes, we have small d is equal to d by n to the power of 2 by 5. Okay, so this was one question. Now we'll solve one problem on pipe network. So this is a pipe network. For the pipe network, determine the flow in each pipe. So you have seen it A, there is an inlet of 100, discharge of 100, then at B there is an outlet of outflow of 20, and at D there is an outflow of 50, and C there is an outflow of 30. So and R value, that is the proportionality constant, these values are given as for each pipe. So we know the basic equation, Q is equal to and in this case n is equals to 2, so R into 2 square. Now for the first case we assume, so we assume that 100 is coming, so 70 is coming going in AB and 30 is going in AC, and now at B, and at B there is an outflow of 20. So what we assume here, so we assume that if we go 20 is going on, so remaining is 50, so the 50 is distributed as 15 in BD and 35 in B and C. Now let's see what 30 is going out, and 30 is also coming from AC. So the whatever 35 was coming from B and C, it has to go to D from CD as 35. So this is the assumption of Q values here. So now we will take the two loops. We will follow the Hardy cross method. So for the first loop, that is A, B and C, if you take this loop, now at AB there is a clockwise flow, so the value of RQ square will be, so what we found that delta Q is equals to RQ square by 2RQ. So this is the formula. So how will we proceed? For AB it will be 2 into 70 square, that is R, R is 2 and 70 is the discharge. So 2 into 70 square, 9800, and the denominator will be 2 into R into Q, so 2 into 2 into 70. For BC it is again clockwise, so 1 into 35 square and 2 into 1 into 35 for the denominator. And for AC, flow is anti-clockwise, so it will be negative, so it will be minus 3600, minus of 4 into 30 square for RQ square, and 2 into 4 into 30 for the denominator, and denominator is always positive. So we get the total sum is 590, and here the total is 7425, so the delta Q comes as approximately minus 13. Now similarly for BDC, you do this for BDC, loop BDC. For B and D it is clockwise flow, so positive 5 into 15 square, 2RQ is always positive, 2 into 5 into 15. For DC it is negative since it is anti-clockwise, so minus 1 into 35 square, 2 into 35. And for CB again it is anti-clockwise flow, so minus, so negative, minus of 1 into 35 square and 2 into 1 into 35. Total sum both sides, ratio we get 5. Now for delta Q in loop ABC is negative and delta Q for loop BDC is positive. So we'll see how we will do the correction. So what we assumed that for if you get negative, we have to subtract from the clockwise flows and add to the anti-clockwise flows. So it is this AB was 70 minus 30, so we get 57. BC we had 30, we had 35 minus 13, 22. Now this was assuming clockwise flow in ABC. Now again, while assuming anti-clockwise and while assuming the for second loop, that is BCD, there was a positive delta Q, but it was going anti-clockwise, so there will be again a subtraction of 5, so it will be 17. Now for AC we will does anti-clockwise, so 30, and you have to add 30, so it will be 43. For BD we have 5, it was 15 before, now we have positive delta, so we add, that's 5 equal to 20. And also here in CD it was anti-clockwise flow, we had positive delta Q, so we subtract, so it will be 35 minus 5 equal to 30. So this is how we obtain the revised flow values for the different pipelines. Now we again do the same procedure. Again we take the loop, we found RQ square, again the direction will be same only, we won't be changing the directions. So here the delta Q will comes as 1, and for loop BDC delta Q comes as minus 3. So we do one more round of correction. So since it has come as positive for ABC, so we'll add to AB will subtract from AC, and for BC what we have, it was 17, so 17 minus 1, it was clockwise, so we add 1, so it will be 18, and then again for anti-clockwise it was negative, so we again add, so it is 21, and similarly so it will be 20 minus 3 in BD and 30 plus 3 in CD, since it's anti-clockwise. Now the reverse flows, we again do the same method, find delta Q, it is less than 1, approximately 0, and for less than 1 also for BDC. So the final values will be these values, so approximately, so the final values in each pipe will be this. So this is a very efficient method for calculating the flows in each of the pipe. This is one triangular pipe. This is a question from GATE 2017. So what is given? It is a discharge Q is given. It is coming as 100 at U. The head loss in each pipe is RQ to the power 1.8 with the variables expressed in a constant set of units. The value of R for the pipe AB is 1. For R, AB is 1, and for pipe BC it is 2. If the discharge supplied at point A is 100, is equally divided between pipes AB and AC. So 50 is going 50 is going to AC. Is going to AB and 50 is going to AC. The value of R for the pipe AC should be, so we have to find the value of R for pipe AC. How do we find that? So first the relation is given is HF equal to R into Q to the power of 1.8. Now QAB is equal to QAC is equal to 50. Now if this is 50, now we have to see for continuity equation. So 50 is coming in this side, also 50 is coming in this side. Now at C, discharge of 30 is going out. So what will be the discharge here? It will be 50 minutes, 20 is going in. So now 50 is coming, 20 is coming, so total is 70. So this is balanced. Balanced set of discharges, we found that. Now what we have to do, we have to head loss in the closed loop is equal to 0. So sigma into R of Q to the power n is equal to 0. Okay, sigma into so what is R for AB? It is clockwise. R is equal to 1, Q is equal to 50 to the power 1.8. For BC it is anti-clockwise, so it will be minus of R is 2 into 20 to the power 1.8, and for AC it is again anti-clockwise, so again negative, so and we have to find R into, so what we get, R is equals to 50 to the power of 1.8 minus 2 into approximately comes 0.62. So this is how you solve this kind of question. This is a gate question. Okay, let us solve one more gate question. So this is gate 2019. So two identical pipes are used to withdraw water from a reservoir. So case 1, they are fed in series, and case 2, they are connected in parallel. And in both cases they discharge freely to atmosphere. Assume friction losses, say for both. So find Q1 by Q2, that is discharge in QS by Q, discharge in series by discharge in parallel. What will be the ratio? Now for series 1, what we have, Q is equals to Q1 plus Q2. Now HF is equal to F and Q square. So you have to sum both these terms. So you have seen that both the pipes are identical, so D, L, HF, everything will be same, so it will be 2 into d to the power 5. The total discharge is this one. Sorry, this is for parallel connection. Now for series connection, what we have, HF1 is equal to HF2. So if we from based on HF1 only, so we have, since we have assumed the same, HF is equal to for series HF. So 2 into HF, total head loss is equal to 2 into HF. So so Q is equals to so QP versus QS, so QS by QP is equal to 2, and this will come as say total head loss will be 2 into FL cube squared by 2g d to the power, this is in series. Now QP is equals to 2 plus Q2 . So the correct answer is 2.83. I hope this was clear. So this is all for today. We will meet again in the next class. If there are any doubts, you can ask.